Let T of x1, x2 is given by this. So this is a transformation. We need to show T is a one-to-one linear transformation. Then we need to see if T maps R2 onto, okay, one-to-one and onto R3. So this mapping can be written in this way, this transformation. So T of x1, x2, we can write in this way in vector notation in vertical. So this is the case, is 2x1 minus x2, x1 plus 3x2, 5x1 minus 2x2. And this vector is, in fact, we can write in this way. So we got x1, x2 that goes here, and just the coefficient now, 2, negative 1, 1, 3, 5, negative 2. Okay, so this transformation is in fact given by T of x, because vector x, T of x equals ax. So since it's given in this way, we can write in this way, T of x equals a of x, where a is the standard matrix. So this is indeed a linear transformation. Okay, linear transformation because we can represent this by this standard matrix. Now we need to show T is one-to-one linear transformation. So look at the columns of these two, of this matrix. These columns are linearly independent, because whenever we have only two vectors, if one is not constant multiple of the other, then they are linearly independent. So T is a linear transformation with the standard matrix A, or since we got a matrix A, this is a linear transformation, and the columns of A, the columns of A are linearly independent. I'm writing Li, linearly independent. One column is not a multiple of the other. Okay, since the columns of A are linearly independent, let me put since the transformation T is a one-to-one linear transformation. So because this matrix got two columns, and these two vectors, or these two columns, are linearly independent. Okay, now next we want to see if T also, T maps R2 onto R3. So for this one, so onto R3 means for any vector in R3, any vector means we have, let's say, B1, B2, B3, a generic vector that's in R3. Can we find x1, x2? Okay, for any vector, can we find x1, x2 in R2? For any vector, can we find x1, x2, so that when we map in this way, when we multiply this by A, we get this vector? Is that possible? It's no, because there are only two columns, or only two vectors. To generate a vector like this, okay, we don't need this. To generate a vector in R3, we need three columns, three linearly independent columns, by the way, or we need three pivot positions, okay, in the row. So we can have one, maybe here two, but we have only two columns, so there is no way we can get three pivots rows. Okay, this is going to be 0, 0. we might have just one pivot. We cannot have three. In fact, any vector in R3, to generate any vector in R3, we need three vectors. So we got only two columns, so only two vectors, so not one to one. So since the columns of A are the number of columns, okay, number of columns A are only two, T is not onto mapping, okay. Note that one warning: we might have three vectors, but if they are linearly dependent, we still can't, it can't be onto. We have to have three linearly independent columns, okay. But in this case, we don't have enough vectors. In fact, we have only two. Since the number of columns of A are only two, or there are only two columns, only two vectors, not enough to generate a vector in R3, so not onto mapping.